Okay, the next topic in carboxylic acid derivatives is, let's talk about the hydrolysis um, of each one and the mechanisms. Remember that a carboxylic acid derivative has basically the Y group attached to the carbonyl, and it undergoes hydrolysis with either acid and water, or it can undergo hydrolysis with base and water. Either way, what you're going to do is you're going to form in the end, the carboxylic acid, and then whatever the Y group is usually then has a hydrogen attached to it. If it's in basic conditions, we'll need to do a then H plus H2O step. So what I'd like to do is to go through the base and acid hydrolysis mechanisms for the four different derivatives. So let's start with an acid chloride. So if you have an acid chloride, you really do not need base or acid to make this reaction go. What you can actually get away with is simply water. And what will happen is that the Y group in this case is a chlorine or a bromine. And because the chlorine is withdrawing electron density from the carbon, it makes that carbon more delta positive and more susceptible to attack by the oxygen. So the oxygen can come in and attack on its own. That will make an O minus. The entire water molecule will add, and you will end up with the oxonium ion with the chloride. Now, there's a couple of mechanisms that are proposed in textbooks at this point for what happens in this mechanism. First of all, we could think of this in terms of the O minus coming down and grabbing the H plus. And if that was the case, then we would end up with the two OHs and the chloride. And in that case, what we would then do is either one of those OHs, the pair of electrons could move here, the chloride could get kicked off, and you would end up then forming the carboxylic acid and in the process, in essence, losing HCl. So that's one way to write this mechanism. The other way that you'll oftentimes see is they'll say the O minus just comes back down, the chloride gets kicked off. What that ends up doing is reforming the carbonyl, and now the oxonium ion is present, and then you lose the H plus to form the final carboxylic acid product. So I lost the Cl first, the Cl minus, and then I lose H plus. Both of these mechanisms, as far as we're concerned, are correct. I'm not quite sure which one is the true mechanism. I actually I'd like to study this in the future using something like an oxygen, a water molecule that has that's labeled with something like oxygen 17. Oxygen 16 is the normal isotope of oxygen, but you can buy oxygen 17 labeled water. And one of the things that would happen is that if you think about carrying through that label, you would end up adding the oxygen 17 labeled oxygen to that acid chloride, and then if mechanism 1 occurred, you would basically end up with 100% of the oxygen 17 in that final product. So there, you wouldn't lose, you would end up with 100% of that. On the other hand, if it went through the second mechanism, what you would end up with is the hydrogen could either be lost from the oxygen that wasn't labeled, or it could be lost from the oxygen that is labeled. So in the end, you would end up with only about 50% of that oxygen as oxygen 17 labeled. And so simply by running this reaction and adding to it oxygen 17 labeled water, which I inherited several $1,000s worth when I came here now 26 years ago, and I recently purchased some. Oxygen 17 is very limited within the world. So if you did this experiment, you could just simply take a mass spec of these two products and find out how much of it contained oxygen 17 versus how much of it contained, if only 50% of it contained oxygen 17, then the other 50% would, the other 50% would have the oxygen 17. If 100% of the final product was, then you could do that, because you would lose the chloride to form either the carbonyl. Now, in these two cases, what you would end up with is you would end up with oxygen 17 in both cases. So I'm going to take back my 50%. So you would end up with oxygen 17 in both of those, where it would be exclusively in the OH position. So the first thing you would do is check by mass spectrometry to make sure that you ended up with oxygen 17 in the two products. So you would have a 50% and you would have another 50% in that position. But then if you did oxygen 17 NMR, you would be able to tell the difference between the oxygen that is in the carbonyl position versus that in the OH. So one of these days I'll get around to doing that experiment, because we're going to see that these two mechanisms can occur in any of those reactions. So that's the hydrolysis of an acid chloride. You don't need acid, you don't need base, you just need water. Now let's go to the acid anhydride. So with the acid anhydride, the acid catalyzed hydrolysis would be to take the H plus and protonate one of the two carbonyls. We usually use acid anhydrides where the two R groups are exactly the same, so it doesn't matter which carbonyl we protonate. If we did it this way, what we would end up doing is we would end up protonating the carbonyl group on the right, and then the water would come in and attack that carbonyl with the pair of electrons going up to the OH, so that, I should probably write these out as equilibrium arrows. Then you would end up with the carbon with the OH on it, and then the oxonium ion adding. So this is under acidic conditions, so we'll always have acid present. Then we're going to lose the H plus. Once we lose that H plus, we're going to end up with that molecule. It's not a hydrate because there's only one R group in the carboxylic acid part on the other side. So then what we would do is then we would go ahead and protonate. We would have the acid protonate, and in this case, if it protonates either one of the two OHs, I'm working backwards. So I would go ahead and have it protonate the carbonyl, the oxygen, basically the ester oxygen, so that it forms that oxonium ion. And now what's going to happen is we're going to have this pair of electrons from either of the OH groups come down there, and then we're going to lose the carboxylic acid part, so that we would end up forming the carboxylic acid, and the other molecule would then be a carboxylic acid as well. and we would lose H plus in that process to regenerate the catalyst. So when you hydrolyze the carboxylic acid anhydride, you end up with 2 equivalents of the carboxylic acid. So that would be the acid catalyzed hydrolysis. The base catalyzed hydrolysis with the O- would basically be that the OH- would come in and attack the carbonyl directly. We would end up with an O- with the R group, with the OH group down here. And again, when you form that O- by attacking a nucleophile, the O- would want to come down. In this case, the carboxylate group would be the leaving group because it's a weak base, because the carboxylic acid group is strong. And so what we would end up doing is having that group be the leaving group, so that we ended up with the O-, and then we would end up with the carboxylic acid group on the other side when the carbonyl reforms. So under basic conditions, you would form the carboxylate. Most likely then the excess hydroxide would come in and deprotonate that carboxylic acid, so that you would end up then with 2 equivalents of carboxylate in that hydrolysis reaction. And then after the base is done reacting, you would then add H plus H2O to it, so that you would again cleave the anhydride and now produce your 2 equivalents of the carboxylic acid. I'm just going to rewrite this one over here. So that's the basic hydrolysis of the acid anhydride. Now the next one is an ester, and so if you have an ester, I'm going to write an R prime group there just to indicate that the 2 alkyl groups don't have to be the same. This mechanism is going to be slightly different depending on whether it's acidic or basic. So under acidic conditions, what we would end up doing is we would end up protonating the carbonyl. And then the water molecule in the hydrolysis would come in and attack the carbonyl and have the pair of electrons go back up to the OH group. And how many times have we done this? We've done this a lot. We're going to actually continue to do this. So I would end up with that oxonium ion, and then of course the next step is to lose the H plus to form the molecule with the 2 OHs here. Now the problem is that, again, that's not a hydrate because of the presence of this OR group. Now, if I'm going to react this with H plus, if I protonate either of the OH groups, I'm going backwards. So I'm going to go ahead in this case to go forwards, and I'm going to protonate the OR group. So now I have my oxonium ion, and again, this is one of these places where we have 2 possible mechanisms. We could lose the oxonium ion group and form the carbocation, which I'll show again to remind you of this. So we could lose the alcohol part, and if that was the case, we would end up with a carbocation, and then we would move this pair of electrons down and regenerate the catalyst to form the carboxylic acid. Also remember that this does have a resonance structure. If I take this pair of electrons and move it there, so that it more resembles a protonated carbonyl, and that protonated carbonyl then would lose H plus to form the carboxylic acid. So that's one way, that's the longer way of losing the alcohol than losing the H plus, but you'll oftentimes see in textbooks, you'll see this pair of electrons move down here, and just go ahead and do this in one step, lose the H plus and the alcohol so that you form the carboxylic acid, the acid catalyst, and the alcohol. So either one of those mechanisms is fine with me. One's considerably shorter than the other, but they both get the job done, and you'll see these used interchangeably within the within organic textbooks like Top Hat. So that was acidic cleavage. Basic cleavage is a little bit different and requires a little bit of discussion about one of the steps. So if we react this ester with just simply hydroxide, hydroxide comes in, attacks the carbonyl, so that we end up forming the O minus and then the OH along with the OR group. Okay. Now again, I've added a nucleophile to the carbonyl to form an O minus. This O minus would love to bring the pair of electrons back down to it and reform the carbonyl, but if it does that, something has to leave. Which group is the better leaving group? Hydroxide? And remember, there's no acid to protonate anything. So is the hydroxide a better leaving group, or is the OR minus a better leaving group? Well, if you go back, you remember back to the last lecture, the OH minus is a weaker base than the alkoxide. So let's say 9,999 times that OH group will leave, and you'll go back to the beginning. That doesn't get us anywhere. How about that one time in 10,000 that the OR minus group leaves? What happens next? What happens next is the following. We end up reforming the carbonyl, we end up with an OH group, and now we end up with our alkoxide. Again, that's not likely to happen maybe 1 in 10,000 times. I don't care if it's 1 in a million times, because the one time it happens, and the other thing I should add here is we usually need some heat for this reaction to go. So that one time that alkoxide leaves, here's what happens. We have a carboxylic acid reacting with a strong base, and I can write the equilibrium here, won't matter. That strong base, the alkoxide, is going to immediately deprotonate the carbonyl, and that's going to happen 100% of the time, so that I'm going to end up with a carboxylate and now my alcohol. Well, that reaction's not reversible. So that one time you lose the OR minus, you end up with these hydrolysis products, and the reaction cannot reverse itself. So given enough heat, given enough time, every time you lose an OR minus group, it ends up forming product. So eventually, you'll end up with 100% of the hydrolyzed ester, forming the carboxylate. So this is one where this step is not favorable. But when it occurs, this step down here is irreversible. And so that pushes basically the equilibrium all the way to the right. Okay. So different mechanism for base hydrolysis versus acid hydrolysis. Now let me take a moment here to talk about some practical uses of this base hydrolysis reaction. This base hydrolysis reaction is very useful to form things like soaps. What's a soap? Well, a soap was originally made, who knows when, by taking an animal fat or a plant or animal oil. So this is what we call a fat or an oil, because that is called a triglyceride. The triglyceride is basically long-chained fatty acids that have been converted into an ester by making the ester of what's called glycerol. So the alcohol part of this is glycerol. Okay, so glycerol, the triglyceride, has fatty acids. So these could be anywhere from 12 carbon chains to maybe 20-something carbon chains. Some of the chains will have single bonds completely. Remember, those are what are called saturated fats or oils. And some will have double bonds, and some will have multiple double bonds. Those are unsaturated fats and oils. And in general, the triglycerides that are made up of saturated will tend to be fats, and the difference between a fat and an oil is very simple. Fat's a solid and an oil's a liquid. So if you wanted to get a natural fat, you know, if you go to the grocery store, you can probably still buy some lard. I think you can buy Bob Evans lard, which doesn't give me confidence in the restaurants, but you can buy buckets of fat, of lard, and so you can end up with a fat. You can get some vegetable oil, which has multiple bonds down here, so that it doesn't pack as well in the solid state, and it has a higher melting point, and therefore is an oil. A lower melting point, so that makes it an oil at room temperature. So you can end up with the saturated, you can end up with the unsaturated. You can actually convert a saturated fat unsaturated into a saturated fat by reacting with hydrogen and palladium, doing a hydrogenation reaction with the double bond, like we learned about all the way back in the alkenes chapter. If you don't quite hydrogenate all of the double bonds, you end up with the evil partially hydrogenated fats and oils. But anyway, what you do here is, let's say you had a tub of lard and you wanted to make some soap out of it. What you would do is you would treat that with sodium hydroxide. I think sort of pre-chemistry days, you would get your lard or your animal fat from said animal, not living. And then what you would do is then you would use lye or potash. Potash is potassium hydroxide. You would use either one of those. You would boil your fat and your oil with in those two bases, and you would get the glycerol, and you would also then get carboxylates, either saturated or unsaturated. Potash, just so you know, I mean, where did people find potash? Basically, if you burn wood, the residue that's left over has a lot of potassium hydroxide in it. You know, so if you're ever stuck without soap, and who knows the way the world's going now, then all you got to do is get some animal fat or some vegetable oil, burn some sticks, boil the vegetable oil and the fat with some burned up sticks, which would be potassium hydroxide, and you can make some soap. If that was your only problem, then I think you'd be doing very well under those circumstances. This then is this would be a fatty acid carboxylate. It's a soap because you have a hydrophilic. You have your hydrophilic end, which will be water loving. You have your hydrophobic end, which is going to be fat loving or water hating. And then what you would do is then when you mix that, it acts as a soap, because what happens is the hydrophobic end, let's say you got a dirt particle or some grease or oil, your hydrophobic ends all end up surrounding the grease or the oil, and the hydrophilic ends end up soluble in the water. So basically you make what you would consider to be a micelle. And if this looks like a cell wall, yeah, pretty much the same thing, only not with the carboxylic acid, with something like a from a phospholipid type molecule. So that's kind of an aside in terms of where base hydrolysis turns out to be important. This reaction actually has a name. It is called saponification. And notice that kind of soap. Switch a couple letters and you have soap. So saponification is the base hydrolysis of a ester. Okay, so that's acid and base hydrolysis of an ester. The acid and base hydrolysis of an amide would look very similar to this, only it's going to require a lot more heat. So we would take this, we would treat this. If we treat this with acid, it's going to be pretty much the same mechanism as the ester was. You're going to protonate the carbonyl to form the oxonium ion. And then your water is going to come in and attack the carbonyl with the pair of electrons going to the OH group. I should be writing equilibrium arrows here. We're going to end up with the OH group on top. We're going to end up with the OH group on the bottom, only as an oxonium ion. And then our NHR group over here on the side. We're then going to lose our H+, to form, have the two OH groups here, and then of course our NHR group. Now it's time to protonate something. Protonating the OH group just takes me backwards. Protonating the NH group is going to take me forwards. Forming that species, that ammonium. And then, just to make this mechanism shorter, we would then take this pair of electrons, move it here. The nitrogen would be the leaving group. Form the carbonyl, end up with the OH group, and end up with the amine. Now, for those of you who are saying, okay, we've got equilibrium in all of this. At this point, we have a carboxylic acid plus an amine. So what's going to push this equilibrium to the right is the amine coming in and deprotonating the carboxylic acid because the amine is a base. And so we make our friend, the ammonium carboxylate, the ammonium carboxylate, remember, is what happens when you add an amine to a carboxylic acid. Then if you heat that, you would end up making the amide. So this acid hydrolysis is the reverse mechanism of basically forming that amine. Base hydrolysis is going to involve the same type of a magical step, meaning that the hydroxide is going to come in, attack the carbonyl, pair of electrons will go up to the carbonyl oxygen. This probably would be an equilibrium step of some sort. We'll end up with the OH group down here and the NHR group here. Now remember, without any acid present, you're not going to get protonation. So when this pair of electrons moves back down, what's better, hydroxide versus nitrogen? Well, by far and away, the hydroxide is a much better leaving group. We're going to need heat for this reaction to occur. I would say at this point, maybe 100,000 times, you're going to have the reaction reverse backwards to the one time that the amide leaves. So 100,000 times the OH group leaves, one time the amine group leaves, but when the amine group leaves, we end up with the carboxylic acid and an NHR minus group. That is going to immediately deprotonate the carbonyl, and 100% of the time, you're going to end up deprotonating the carboxylic acid group to make the carboxylate and now the amine. And so that's what's going to drive the reaction to completion. This is going to be a much more difficult reaction, so it's going to require a little bit more heat, but that's the hydrolysis mechanism for an amide. So what I've done is I've shown you the hydrolysis reactions for all of the carboxylic acid derivatives in probably more detail than what the textbook does, although the textbook is going to show you those mechanisms throughout the course of the remainder of chapter 25. Okay, so that's where we're at in terms of the hydrolysis of those species. All right, so now let's talk a little bit about anhydrides. Number one, what you can do with them, and number two, how do you make them? So let's do number two first. How do you make how do you prepare acid anhydrides? Two ways. First of all, an acid anhydride is a carboxylic acid anhydride, means literally without water. So we just saw that if we hydrolyzed a carboxylic acid anhydride, what did we end up doing? We ended up forming two carboxylic acids. So when you bring the two carboxylic acids together, you're going to lose water to form the anhydride, so that's why it's called an anhydride, meaning you lose water. It's a carboxylic acid without the water. So you're going to react two of those together. Your choices are, you could do this under acidic conditions. If you do it under acidic conditions, what you're going to end up doing is protonating one of the carbonyls. So I'm going to leave the other carboxylic acid over here intact. And you're going to end up then protonating the carbonyl to form the oxonium ion. How many times have we done this? A lot. Then what's going to happen is the carboxylic acid OH group is going to be the nucleophile and come in and add. So now I'm going to end up with my OH group where the carbonyl was, and now I'm going to end up with the OH with the plus charge with a C double bond O. So I've added the carboxylic acid as a nucleophile. I'm going to lose H plus here. So when I lose my H plus, I'm now going to end up with that species. Next step is to react the acid with one of the oxygens. If I react it with the oxygen of the of what was the carboxylic acid, I just go backwards. So let's go ahead and protonate one of the two OH groups. To make an oxonium ion, what happens next? Well, again, if I want to simplify my mechanism here, which is why I think the book does this, let's just go ahead and bring this pair of electrons here to reform the carbonyl, have the water leave, so lose H plus, H2O, and then what I'm going to end up doing is I'm going to end up then forming the carbonyl. All I did was bring this R group over here, so I can kind of write it like a carboxylic anhydride would look. So I can form the carboxylic acid anhydride that way by losing water and losing H plus. Now, usually we use two equivalents of the same carboxylic acid so that we basically make a symmetrical anhydride. If you wanted to make an unsymmetrical anhydride, like you wanted to make an anhydride that has like a methyl group on one side and maybe an ethyl group on the other, this would not be the ideal mechanism, because when you mix those two acids together, you can think about the combinations that would occur. You would get two of this carboxylic acid forming an anhydride, two of this carboxylic acid forming an anhydride, and then you would get the mixed. So you would end up with like 1/3 of the mixture being the mixed carboxylic acid anhydride. So the best way to do this is to simply say, let's start with an acid chloride, and now let's react it with the salt, the deprotonated carboxylic acid, the carboxylate, and can't react that with a carboxylic acid, but I can react it with an acid chloride. This is now a nucleophile, will come in, so that what I will end up doing then is forming the O- along with the Cl, and now the other carboxylic acid will have added. O- reforms the carbonyl, chloride gets kicked off. So when I lose the Cl-, I end up forming what's called a mixed anhydride. So the best way to make a mixed anhydride is to react a carboxylate with an acid chloride. If you want to make a symmetrical one, you can just use the same carboxylic acid and acid, this kind of acid, as your catalyst. That would be fine. Okay. So let's talk a little bit about reactions of acetic anhydride. You have done one in lab. In lab, here's what we did. We had our para-aminotoluene. And what we did was we reacted that in part A of the benzocaine synthesis with acetic anhydride. The N- came in, attacked the carbonyl, so we ended up with an O-, we ended up with the NH2 with the plus charge, and then the benzene ring. Typically what we've done in the past is we've taken and used the O- to remove the H+. Sometimes you'll see textbooks do that, sometimes you won't. I'll show you why in a minute. Okay, so now I end up with this. Now, when we did this reaction, we did it in a buffer. So if you remember that reaction, we used acetic anhydride along with a mixture of acetate and HCl, which made a buffer of acetic acid and the acetate. Now, what will happen next is the following. This pair of electrons is going to come down, and we're going to reform the carbonyl. You could say, why doesn't that happen over here? I mean, it could. But if the pair of electrons comes back down and forms the carbonyl, which one is a better leaving group? Nitrogen of the amine or the carboxylate? Carboxylate wins hands down, so this pair of electrons moves here. So we end up losing H+. We end up then forming the carboxylate. And then we also form the final product, which was the C double bond O to the NH, which was then para to the methyl group. So that was step A. This was step A of the benzocaine synthesis. So we already did that. And if you're saying, what about the H plus and the carboxylate? Yep, they'll react together to form acetic acid. Now, just as kind of an aside here, the reason that we used in our synthesis, we had a mixture of acetic acetate and HCl. We used that mixture because we basically created a buffer. The reason that we created the buffer was that once we formed the acetic acid, we wanted to deprotonate that acetic acid hydrogen, because if you think about the reaction, if I form this product, that proton would be able to come back over here and protonate the amine, and that would kill it as a nucleophile, because then it would form an ammonium salt. So the idea of the buffer is, what the buffer did was it kind of neutralized the acetic acid that was formed as the product. And by neutralizing it, it prevented the protonation of the amine of unreacted compound. So that's why we use that reaction. And this is a fairly environmentally friendly reaction, simply from the standpoint of when you form the acetic acid, you can collect it and you could convert it back to acetic anhydride if you were going to do another reaction like this. Now, the slide says synthesis of Tylenol. So I could modify this synthesis by reacting para-aminophenol with acetic anhydride. And a lot of times, and this is a really good synthesis of Tylenol. Which of these two potential nucleophiles is going to react with the acetic anhydride? the stronger of the two. Which one of those is the stronger of the two? Remember our periodic table of CNOF. As we go from right to left, we have stronger nucleophilicity and basicity. So which of those two is a stronger nucleophile? The nitrogen. So this is a very easy synthesis of Tylenol, which was acetaminophenol. So that's a very easy synthesis. You can collect up all of the acetic acid that's formed in this reaction and reuse it as converted to acetic anhydride and reuse it again. So it's a very, very simple synthesis that's used to make Tylenol, which is an NSAID pain reliever. Just as another aside, acid. This is salicylic acid. It is a major component of birch tree bark. If you, what people found was sort of as a folk remedy, if they had salicylic acid and they were to, if they had a headache, they would chew on some birch tree bark and magically their headache would disappear. It has one bad side effect in the fact that it tears up the lining of your stomach. So what people found was that if they converted the OH group to an ester, they so-called acetylating it or acetylating it, they formed acetyl salicylic acid. If you remember from first semester lab when we isolated the two of the analgesic components and then the caffeine from the Excedrin tablet, acetylsalicylic acid is aspirin. So what they found was that if you, this should be an OH group, if you acetylated the salicylic acid and made acetylsalicylic acid, it was far less irritating on your stomach lining. Still, if you take too much aspirin, it can have an effect and do damage to your stomach lining. But aspirin is like the most used drug probably in the history of time. But that's where it came from. And then there was a chemist named Felix Hoffman. I think it's a different Hoffman than Hoffman elimination. But he worked for the Bayer company in Germany. This was probably pre-World War II. And then the Bayer company lost the E and made Bayer aspirin. That synthesis came about really from a folk remedy. You can't go around killing all the birch trees to get the bark to cure everybody's headache, plus then they destroy their stomachs, so you acetylate it. And how do you acetylate it? You acetylate it with best way with acetic anhydride. So that's one of the ways to make aspirin, and that's the way it's commercially made. Okay, last reaction that we'll talk about in this video, and then I think we will, in the subsequent video, we will finish up chapter 25 and move into the last chapter of the semester. Yay, chapter 26. But remember, we've got, or you're working on exam 4 in between now and then, so don't get too happy. Is the preparation of amides from esters. It turns out that if you take an ester and you react it with an amine, so maybe I have 3 different R groups here, it's very easy. You probably need a little bit of heat, but what you will end up doing is you'll end up replacing the OR group with the amine, making the amide, and then making the alcohol. So that reaction is a fairly straightforward one in the following way. No acid, because acid will kill the amine. It will turn into an ammonium salt, which is no longer a nucleophile. So again, we have the pair of electrons of the nitrogen attack. So I'm going to form my O-, and my NH group will now, my NH2 group will now add. I'll end up with the oxonium ion, or with a ammonium ion. If you're thinking, hey, I've seen this before, yes. Enamines and imines. The O- then comes down and will remove the proton, so now I will end up with this. All right, great. I don't have any acid, but I do have heat. So that means I can bring this pair of electrons back down. Something's got to leave. Who's going to leave? Well, the OR group is going to leave. What? 10,000 times. The OR group's going to leave, and I'm going to end up right back where I started. That one time that the nitrogen leaves, though, so that one time, what am I going to end up with? I'm going to end up with the carbonyl. I'm going to end up with the NH with the R double prime group, and I'm going to end up with the O-. That then will react with the H+ to make the alcohol. The driving force for this reaction, okay, the driving force for this reaction is not necessarily, there's no deprotonation step in this like there was with hydrolysis of esters or amides. The driving force for this reaction is that the amide turns out to be more stable than the corresponding ester. And the other then issue here is the following. Once I form this alcohol, without acid present, it cannot add to that carbonyl. It cannot add without H+. And there is no H+ present here. Up here, with nitrogen as the stronger nucleophile, it can add. So all of those combinations of things then pushes the equilibrium towards the formation of the amide. So that's how we prepare amides. We can prepare amides from esters, but no acid, just heat. Okay, so that's going to end this video, and we will finish up chapter 25 in the next video, and then move on to enolate chemistry, which will be chapter 26, and will be the end of what we talk about this semester.